All right. So we've just finished up forces, Newton's laws, all three Newton's first, second, and third laws. Um, so now we're going to move into actually starting to talk about it. What happens if your forces, the magnitude of those forces actually change over time. And to do that, we're going to talk about impulse and momentum. Uh, so if you consider the following, okay, we got two different types of momentum problems that we're going to talk about. We've got a collision, which is essentially just a short interaction between two objects. And this is when the particles of a system, they're actually moving together. I mean, you all know what the definition of a collision is, but this is two things hitting each other, and the short duration part is important. Um, these are very quick interactions. The opposite of that would be an explosion. And this is essentially just when the particles of a system actually move away from each other after a brief, intense interaction. So we've got a situation where things are coming together in a collision or they are moving apart during a brief, intense interaction. And that would be an explosion. So the goal is essentially we're going to describe and predict some simple outcomes, but these simple outcomes are going to be from these very complex interactions. You can imagine with everything going on in a collision or an explosion, these can be actually quite intense interactions. But the goal is to move from this complex look to something that we can write out in just some simple equations that will sort of encompass the whole complexity of the interaction. To do this, we'll think about the momentum of an object or the objects before and after. So we're kind of accounting now. We're looking at what's going on before the interaction of the explosion, and then the after picture, what's going on after these things have interacted, and comparing the two before and after pictures. That's actually going to give us a lot of information. So we do need to define what momentum is. And essentially the momentum is just a particle's mass times velocity. We've got it written down here. Since velocity is a vector, you guys should know that by now. Well, and mass, of course, is a scalar. What you can see is essentially momentum is your velocity vector, but it's been scaled up or down by your mass. So you're really just changing the length of your velocity vector, and that's your momentum. Um, the units of momentum, they are a little weird. It's kilograms meters per second. Don't confuse this with newtons, which is a force, right? So the newton is a kilogram meters per second squared. Um, so you can see we are missing the second squared. Here we just have seconds down here. So do keep that in mind. Don't get momentum and force mixed up. Yeah, and then this last bullet point is just the momentum is a particle's velocity vector scaled by its mass. And you can see over here in the picture, we have this velocity vector here. Clearly, we've got a large mass because we've made the momentum vector longer. So I will come up here, change colors real quick. So you can see since the momentum vector is longer, we've clearly multiplied by some sort of large mass since we're multiplying the mass times velocity. There we go. And do remember that just like any other vector, we can break it down into the x and the y components um, if we need to. So think about these collisions. We need to actually think about what's going on in the collision. We're going to slow it down and talk about this brief interaction, but over a long period of time, essentially. We're going to watch it in slow motion and talk about each little piece, even though the interaction itself is happening very quickly. So the duration of a collision really depends on the materials from which the objects are made. So if you play pool, you know that two pool balls, they'll collide and bounce apart really quickly. But if you're, jumping on a bed as a child, that interaction between you and the mattress is much longer because the materials between a pool ball and a mattress are very different. So the materials that these things are made out of, that's important. The collisions generally are on the order of milliseconds, so these interactions are quite brief. The harder the objects, just like the pool balls, the shorter the contact time. Okay. Uh, and again, we're coming back to this idea of these molecular bonds as springs. The whole idea of like where these forces are coming from. This is just the molecular bonds. We have an object coming in, and then those molecular bonds between the two objects, those compressions, and then they're pushing back to decompress to return to the original shape. Those two forces equal opposite kind of thing. That's where these collisions get their energy from. So of course this will be an action reaction pair, and you can see up here in the top right we've got this tennis ball. It obviously had an initial velocity coming in, and then it's gonna bounce off this tennis racket, and its final velocity is going to be in the opposite direction. And then just at a atomic level of this, you can see we have object A, object B, and here's their molecular structure. So the idea is that when these two things interact, we've got this object A here. We can tell it came in this way, moving to the right, and started pushing against object B. And you can see the compression here uh, in the molecular structure, and that compression is going to provide that equal opposite reaction the other way, which in turn is going to cause object A to shoot away in the opposite direction. All right, now let's think about that interaction here in this middle piece of the whole thing. This is we're going to introduce the idea of an impulse. Uh, so if you look here on the plot in the bottom right hand corner, essentially what's happening is we have no force exerted because the object actually hasn't hit. You'll notice on the x-axis, we're moving with respect to time to the right. So this is over the course of the milliseconds of the interaction, we're going to plot how the force changes. So here we have nothing because there's no interaction. Right, and believe it or not, that says interaction. So the idea here is these two things are barely going to touch each other at the beginning of the interaction. So that would be here. There's maybe some minute amount of force between the two, but just like the tennis racket and tennis ball, that tennis ball is going to start pushing in, or the other object is going to start pushing in. And the more, it's just kind of like static friction. The more you push in, or the more object A pushes in, the more object B is going to resist. So we see this is the object A is pushing in more and more. That means we're going to have that resistive force. So here's object B's compressing. Then we get up here to this peak. This is the peak interaction when there's maximum compression. Okay, then past this point, the object that's being compressed, so like object B up here in our molecular model, it's going to snap back to its original position and then sling object A away. So that's going to happen. And as it slings object A away, there's less and less interaction, which means that force starts dropping. It's smaller and smaller until once again, the objects are not even interacting anymore. So there's no interaction here either. So you'll see that this is a force over time, right? Because we started with zero force, the force increases, peaks, decreases, and then gets to zero again. So over this short period of time, we actually don't have a constant force anymore. It's actually a function of time. But we can still use Newton's second law, as you can see here. We sum up the forces set equal to ma, and in this case, the only force we have is just this impulsive force, which is a function of time. So Newton's second law will still work. It's just our force changes over time. All right. So it turns out you can actually write Newton's second law in terms of momentum. So we've been talking about it here in this first piece, F equals ma. But what's really cool is we can actually tweak it just a little bit, and then we get a change in momentum. So the whole idea here is, well, let's just rewrite acceleration as dv dt. That's just change in velocity. Well, if we do that and we distribute our mass into the derivative, we can totally do that. It's a constant. Well, look at what we have. We have the rate of change over time of momentum. Okay, so really this just comes down to the force equals the change in momentum over time. dp dt. Okay, so this is just another way to rewrite Newton's second law. From this, though, what we can do is we can take this first piece here, so F equals m dv dt, and just move those bits over. And this works if your derivative, if our dv dt is continuous and differentiable. And because we're dealing with the natural world, our dv dt is continuous and differentiable. Therefore, we can break it up and treat it like a fraction. So we're going to leave the m dv on one side and just multiply the dt over. Okay, so we've done that. That kind of looks like pieces of an integral on the left and the right. So let's integrate it. So this will be the integral of m dv dt, and we can integrate with respect to time over here on the right. Now remember, we need to go from some initial velocity to initial time. We've got that here, initial velocity, initial time. They need to line up with each other. Then we also need to integrate to a final velocity and a final time. And those also need to line up with each other. Well, here, this is easy because that's just an imaginary 1 in there. So the integral of dv is just going to be final velocity minus initial velocity. We can multiply the m back through. Okay. Well, this is just the final momentum minus the initial momentum, and we know how to represent a final minus initial. That's just delta p. Now this other side on the right, we can't actually integrate because we don't know what function this is. This could be any function. This could be any function. Okay, so we're going to leave it just as an integral. All this is saying is that whatever the function looks like, the area under that over that short collision time, that's what we're after here. We just want the area, it equals the change in momentum. Now what we can do is we can actually give this a name. Okay, now this time integral of the force, the change in momentum, this is actually going to be the impulse, and we're going to represent it as J. All right, so we know that the integral of f of t over time equals J, and we know that this is just dp, the change in, or delta p, this is the change in momentum. And again, it's just the area under that curve that we've already talked about. So essentially, whatever's under here during that interaction, that growing force that peaks and then decreases again, whatever is there under that curve, that's responsible for changing your momentum. You can see that J, the area under the curve, equals delta P. All right, so the impulse momentum theorem, which is exactly what we were just talking about, the change momentum equals your impulse. Okay, so we've got this from the previous slide. Now let's talk about this a little bit. So we have this impulse. Okay, we can rearrange since delta P equals final minus initial. And it turns out all this is saying is that your final momentum if you have some sort of interaction, what you end up with is just what you start with. So this is our start, okay, plus some interaction, okay? Now that interaction is what's responsible for changing your momentum. Okay, let's look over here at these plots and talk about what's going on. So we have the impulse momentum theorem, delta P equals J. The whole idea is we start with a before, and then we look at what happens after. So we have this ball, it's heading toward a wall, as you can see here. Notice it has a positive velocity, okay? Now it's going to start interacting with the wall shortly. But while it's flying toward the wall, if you look at the middle plot right here, there's no force acting on this ball. It's just flying through the air. Obviously, there's gravity and stuff, but the whole idea is we're looking at just right before the interaction, right after, kind of ignoring everything else. Okay? So during this time, the ball's flying to the right toward the wall. No forces are acting on it. So as it gets over here, it's going to start compressing, right? You can see here. And then eventually it's going to peak. And that's where the plot bottoms out here. And the reason this force plot is negative was because if you look up here on my plot or on my picture, the force is actually in the negative x direction. That's why down here we're going to get a negative area. All right, so you can see as the ball starts getting squished, when it gets to the bottom here, it's fully squished, and then it's going to start spreading out again. It's going to try to reform to its original shape and bounce off the wall. So as it starts leaving the wall, there's less and less interaction. I guess you could think of it as like there's less and less normal force as it starts leaving the wall. Okay, now you'll notice once it stops that interaction and the force gets back to zero, afterwards, it's actually heading in the negative direction. Okay, it's moving away from the wall now. Now, if we plot the momentum and not just the force, we have a positive momentum. You can see on the bottom plot here. And then as it starts hitting the wall, it doesn't just lose all of its momentum at once. It gets squished, so that momentum slowly dissipates and then hits zero and then grows in the negative direction. So you can see here I've got these lines lined up to where the interaction starts. And right here, when the momentum is zero, that is maximum compression, and then it starts to leave the wall because it's trying to reform to its original shape. Now, once it actually has left the wall and is flying in the opposite direction, because its velocity is constant, it's going to have momentum again, just flat line. It's constant momentum, just negative now. And we can actually think about this in terms of a bar chart. So we have, as you can see here, I'll change to blue. As you can see here, we have some positive amount of momentum. Okay, and then we're going to add this negative momentum in the opposite direction. Okay, that's where this comes in. You'll notice it's quite negative. It's a big force. It's a big impulse. And then when we add these two things together, what's left over is this piece here, and you'll notice it is also negative. It started positive. The momentum of the ball started positive, but then after that negative impulse, the overall momentum becomes negative. So the impulse momentum theorem, this is important, only applies during the brief interaction between the object. So of course there's gravity and all this other stuff going on. We're not worried about that right now. We're just worried about the brief interaction. So only the momenta just before and after the collision is considered. Fun fact, momenta is actually the plural of momentum. So if you have two different situations, you actually have momenta, not just momentum. So let's look at a couple of quick examples. So we have a 100 kilogram, nope, just a 100 gram rubber ball is dropped from a height of 2 meters onto a hard floor. Okay, so we've got that in figure 10 here. We've got the impulse. That's the ball's actually feeling when it hits the floor. Um, so here it does say this is the force, but that would be the impulse. Okay, so we're dropping the 100-gram ball 2 meters onto a hard floor. We've got some impulse and the ball bounces back. So how high, as the ball bounces back, how high does it bounce? Okay, well, first we need to model the situation, which we have over here. We have a model and visualization. We also have the impulse chart here, the bar chart. Okay, so let's think about what we got here. We know that we're going to have some sort of change in momentum, and we're going to have that change in momentum. It's going to equal the impulse. Now the impulse is going to be this area under the curve, right? We got to integrate from the initial time to the final time of the impulse. Okay, and that's going to give us J. Okay, so we have everything we need. We have our impulse, we have our before picture, our after picture. We're good to go. Now, to determine what our initial momentum is, because we need a final and an initial. So we need initial and we need a final. Okay, well, we need to know what the speed is right before it hits the floor. Now we can do that with kinematic equations that we've been using. So we know this thing has been dropped from a height of 2 meters, okay? So given that it's assuming dropped on Earth, we know what gravity is. We can do some basic kinematic equations, stuff that you should be familiar with by now. We can simplify our kinematic equation, which I'm sure you guys remember. So from that initial drop height, we don't have time, but we can still calculate its final velocity, which it turns out when it hits the floor, we're at negative 6.26 meters per second. So we could actually go ahead and write, this is our initial. This would be, let's see, 0.1 kilograms times velocity negative 6.26 meters per second. And you'll notice that our units do work. We have kilograms, meters per second, so that's looking good. We can calculate that later as needed. Let's see. Now we just need to, we got our initial momentum here. We just need to calculate that impulse. And luckily for us, it's triangle. So it's just going to be 1/2 the base times the height. Oops, I'm labeling these wrong. Let me try that again. 1/2 the base, because the base is time, times the height. Okay, and that's going to give us 1.2 Newton seconds. I know that the impulse here seems kind of weird, but that's fine. Newton seconds is totally fine. Now we just have to use the whole idea of our final down here, P final. It's just the initial plus J. All right, so we're going to plug in our initial momentum plus the impulse. So here's PI plus the impulse J, and that's going to give us our final momentum. Okay, so this is going to be the momentum going up in the positive y direction. Now remember, we wanted to know what height this thing reaches. We don't want to know its final momentum, but we need its final momentum. Okay, so we can rearrange really quickly. P final equals mv. So we want to know the velocity here. So we'll just solve for that final velocity. That's just the momentum divided by mass. We can plug that in. We know what that final momentum is. We know what its mass is. The mass is not changing. It turns out as it leaves the floor and leaves that collision, it's going upwards in the positive y direction with a speed of 5.74 meters per second. Okay, So you'll notice that the rebound speed is less than the impact speed. That's expected because on the way down, it had a gravity assist. On the way up, doesn't have that gravity assist. Um, so now all we need to do is just figure out how far up it goes, and we can use the same kinematic equation. We have the initial speed, uh, then also is going to be negative g, so minus the 2g delta y. Okay, we can plug things in and solve for delta y. We know that our initial velocity, or initial height in this case, is starting from the floor and going up. We can just say that's 0 up to its final height, which would be y3. And we can solve for that, just some algebra, and it turns out the ball bounces back to a height of 1.68 meters. All right, so because we've talked about kinematic equations so much, I'll skip over some of the algebra there. I want to emphasize the momentum parts and not the kinematic equation parts. So I do encourage you, if you want to pause this, go through some of the algebra, refresh yourself on the kinematic equations if you need to. But the main takeaway here is literally just the impulse momentum theorem, because that's at the heart of this problem. Okay, let's talk quickly about the conservation of momentum. This is actually really cool. One of the most fundamental ideas of physics, but it gets mathy. Okay, so we know from Newton's second law, in terms of momentum, the force equals dp dt. Done that, no big deal. So that's Newton's second law, but what if we apply momentum to Newton's third law? Okay. So remember, Newton's third law is you got one force this way, you have the same force, but in the opposite direction, and it's negative. Okay, so we know that if we have one force, so from object 1 here, so we have object 1, and it's going to act on object 2, right? Because we're talking about between two objects, because that's Newton's third law is always an interaction. Okay, but then we also have object 2, which is going to act on object 1. Okay, so we have 1 on 2. We know that the reaction to this action is going to be negative, so it's going to be negative 2 on 1. Okay, well, that's all well and good. We have these two definitions of momentum 1, momentum 2. But we know that we can add these two things up. We know we can add P1 plus P2 to get a total momentum. That's totally fine. If we want to figure out what the total momentum of a system is, we can do that. All right, well, I can do that here. Now we can talk about adding P1 plus P2, or we can talk about adding the derivatives. It's going to work the same way. We can add them together, then take the derivative, or we can take the derivative of them separately. But if we just wanted to see what happens to the total momentum over time, okay, so total P O over time. Let's just say we're curious about that. We can add them up, take a derivative. Okay, well, this equation here, we know from the previous line just says, well, this is just F1 on 2 plus F2 on 1. But we know that those two things are equal opposites, so we know that this has to equal 0. So far, it's pretty trivial. This is just saying that if you add up the momentum from the equal opposite reactions, you get 0. Well, we can actually take this first piece here, we can multiply the dt over all the way over here to 0, as you can see I've done here. So we've took the first piece, the d total, and then I've multiplied the dt over to the 0. Well, we can integrate that. The integral of d total momentum here, well, that just gets rid of our little delta. or a little d out front. Well, that's just p1 plus p2. That's a trivial integral that makes a little differential go away. Okay, well, if we integrate 0, well, that 0 is a constant. We integrate 0, still get 0. Okay, because we can pull the constant out front, but whatever comes out of the integral, it's still going to be multiplied by 0. But because it's an indefinite integral, we get this nice plus c. So let's think about what this means. So this means actually the sum of the total momentum over the time of the interaction is constant. So you see what happens here? We added up these two forces. They were equal and opposite. Okay, so we summed the forces. They were equal opposite. So we know if we write these forces in terms of their momentum, this cancels out. And then if we do just some basic calculus, it turns out if we add the total momentum in the system, so P1 plus P2 is constant. That means your momentum is not changing. No matter how many momenta you have, you add them up, they're always going to equal some sort of constant. So the big conclusion here is essentially the total momentum before and after a collision is the same. And we know that because the derivative is my second step here. So here's my third step. My second step, this is super important. The derivative equals 0. That means there's no change. So whatever you start with is what you end with. Because the derivative is 0, there is no change. So you can look down here at this very last line. Okay, here's my total momentum at the beginning. Momentum of object 1 plus momentum of object 2. Because the derivative, the change of momentum is 0 in an isolated system, whatever that total is I start with, I have to end with that same amount. So here's the big takeaway. Now, I want to generalize this to lots of particles. And it gets pretty mathy, but it'll be a good time. Okay, so let's say we wanted to generalize this to a million particles if we wanted to. We know that the total momentum of this system is going to be defined where we just add everything up. So I'm using a capital P here for total momentum. So the momentum of the whole thing, we just start adding all these individual momenta up. You can see I've done that here with my P1 to Pn. And I can simplify that just by saying, well, it's the sum of all the momentum. Yeah, that makes sense. You can think about it in a situation like this. So we have this system where we have 3 particles, but we could do this with 1,000,000 if we wanted to. So each particle, like particle 1 here, it's got 2 forces acting on it, and it's also acting on 2 different things. This object 1, particle 1, it's acting on particles 2 and 3, and at the same time, particles 2 and 3 are acting on it. So you'll notice particle 1 does not act on particle 1. Okay. Same thing with like particle 3. It doesn't act on itself. It's only interacting with other things in the system. Okay, so we can add all these momenta up, and that's our total momentum of the system. Now the question is, how does big P change over time? Okay, well, we can take the derivative of it. Okay, so if we take the derivative, and I'll do that here, if we take the derivative of big P, well, that means we need to take the derivative of this side. Okay, and I've done that here. Well, since this is a summation, I'm taking the derivative of it. I can actually distribute the derivative to each individual piece inside. Okay, you can see I've notated that here. So it's just the sum of the derivatives of the individual p's. Now wait, let's look at this. We have a definition here. This is just saying for our kth particle, first, second, third, 27th particle, whatever k is, whatever particle we're looking at. Well, dp dt for that particle, well, that's just the force acting on that particle. Remember, we can rewrite Newton's second law like this. So really, we're just looking at Newton's second law for each individual particle. But because we have lots of particles, we need to add all those forces up, okay? So that's what's happening between this step and this step. We're just adding all those forces up within our isolated system, okay? And then that's going to tell us, because all this equals dp dt, that's going to tell us how the total momentum changes over time. Okay, well, this is a sum, you know, the million different forces or million different particles that we have. This is the summation, sigma fk. But what about just one of them? What if we wanted to define just the forces on one particle and not sum them up just yet? So the forces on just one particle, on the kth particle, well, that would just be the interactions with all the other particles and any external forces that we have. Okay, so here's how we're going to notate it. Here's how I'm saying, here's our interactions with all the particles. If you look over here on the right, so the summation here is essentially just like, okay, particle 1. Well, we've got the interaction between particle 1, particle 2. We've got the interaction between particle 1, particle 3. Then we also have interactions between particle 2 and particle 3. That's the idea here. So if we're just going to look at one of these, like particle 1, we're just summing all the interactions except the interactions with particle 1 with itself. That's why we have that's why we have this notation right here. J can't equal K. That just means that's a shorthand way of saying like the particle can't interact with itself. We can't have 1 equals 1. We can have 1 equals 2, 1 equals 3, but we're not going to think about the particle interacting with itself at all. Therefore, J and K have to be different. So even if we had a million particles in here, this summation would be looking at adding up all those interactions except with the particle in itself. Okay, so we have all those interactions within our system added up, essentially within the box over here on the right. But then we also have to add the external forces acting on this one particle we're thinking about. So that's going to be gravity and everything else. All right, so remember, this whole equation is just for one particle. Okay, we want to talk about the forces on all the particles added together. So what we can do is essentially take all these forces on one particle. Remember this previous line here is just one particle that we're talking about. So we can add all the forces acting on this one particle. Okay, and that's going to simplify, or we can at least distribute the sigmas to say this is a really gross statement to talk about the change of the total momentum. Because remember, that's what we're after. We're after the change in big P over here. So now we could talk about the change in the total momentum, and that's going to equal all these weird summations. We're summing up the stuff happening inside the system. We're summing up all these external forces acting on the system. It gets gross, but it's going to simplify to something nice. Okay, so let's finish this up. So here we have all these interactions. This is from the previous slide. But remember, in an isolated system, think about the forces. Okay. In an isolated system, we have F1 on 2 equals F2 on 1, but it's negative. If we add those things together, they're 0. So it turns out in our box of objects we're talking about, right, we got all these interactions between all these particles. That's the stuff here in red. Okay, this is the isolated system in the box. If it's isolated, we add up all the action and reaction forces, they're always going to cancel out. So it turns out those interaction forces are just 0. So that really complicated term just goes away. And look at what we're left with. We're left with just the external forces. So it turns out, now the sum of the external forces, that's just the net force. That's just the net force like this. There we go. So really, we're just talking about the forces acting on the system. This red, everything in the red box, all those summed forces, that's 0. And we only care about the external pieces. And we did all that math to show that this is what's going to happen. So essentially, in conclusion here, the change in the total momentum, big P, over time, really is just those external forces added up on your system. So yeah, summed up right here. The rate of change of momentum is equal to the net force applied to the system. So not the net force in the system, the net force applied to the system. However, if we are thinking about an isolated system only, so if we're thinking about the stuff up here in red, in an isolated system, well, the net force is 0 on an isolated system, right? So that means like this F1 would go away. That means the F2 would go away in an isolated system. In that situation, dp dt is 0, and the total momentum doesn't change. So this is the law of conservation of momentum. This is huge, big thing in physics. Okay, the total momentum of an isolated system, that's important, is constant. Okay, so interactions within the system do not change the system's total momentum. And that's because we've got those action-reaction pairs. So this is super useful if you're launching satellites or doing things in space. You always have to think about the conservation of momentum. It's also something that you can use in a little bit. We'll talk about like rocket thrust, and that's a whole conservation idea. So therefore, the big point here is in an isolated system, your final momentum and your initial momentum, what you start with, what you end with, they're the same. What you start with is what you end with in an isolated system. And this is a big idea in physics, and it's very useful. It shows up in a lot of places. And now I can't advance my slide. Whoops, there we go. Perfect. Now, something you need to think about when you solve momentum problems. You're in charge of selecting your system. Okay, you get to do that. It's kind of like when we select our origin in kinematics problems or force problems. You want to select a system so that the total momentum is conserved. Because if you draw your box around the wrong part of the problem, you won't actually have conserved momentum for your situation, and then that could make things very tricky. So let's consider over here on the right, let's consider this ball being dropped and bouncing off the floor, or essentially bouncing off the earth. So the way it's drawn up here in part A, we see that the momentum is not conserved. Okay, so the momentum is not conserved. Okay, now the question is, why isn't it conserved? And we're talking about the situation here where we have just the ball as our system. Okay, so the momentum before the collision is negative. Okay, the momentum before is negative because in the before situation is moving in the negative y direction. Okay, and this negative value, so we have negative p in the beginning. Okay, well, this is not equal to the momentum after the collision, because after this ball bounces, okay, so after it bounces, it's going to be going up in the positive y direction. So then all of a sudden we have this positive final. So notice we have a negative on this side, positive on this side. Those things do not equal each other. That's because we drew our system as just the ball. However, if we consider the total momentum, so big P, if we consider the ball and the Earth, then the total momentum is conserved. Okay, so essentially what's happening is the Earth ball system, as they interact, and the ball changes its momentum from negative to positive, well, the Earth actually is going to have this tiny, 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 immeasurably small interaction as well. So the Earth's velocity is going to change a little bit. So it's going to go from a velocity of like 0, the ball's going to hit it. Then the Earth is going to move this in so tiny amount, like it's so small we can't even measure it. But in theory, the Earth will move and sort of make up for that change in momentum of the ball. So essentially, as long as you add up the momenta of both at the beginning, they have this interaction and the ball goes up, the Earth has to counter that change in momentum for the system to have a zero change in momentum. So essentially, the Earth does indeed have a momentum equal and opposite to that of the ball. But remember, momentum is mass times velocity. So because the mass of the Earth is just so big, it doesn't have to do a lot of moving to make up for the ball. The Earth is just so massive that it only needs to move with just an infinitesimally small velocity to match the ball's momentum. But the whole idea here is that, in fact, it's conserved. Momentum is conserved if you draw the correct system. And you can see here on the right, we've drawn this system including both objects interacting, and in this situation, momentum is conserved. So let's summarize really quick. There we go. So the impulse, whoops, there we go. So the impulse, which is essentially just added to the initial momentum of an object, that's what gives you or changes the momentum to the final momentum of an object. Okay, so this J value is our impulse. The impulse momentum theorem, which you can see here, this applies only to that brief interaction between the object and whatever it's interacting with. So I guess we could say the objects, since it is an action reaction. Okay. However, in an isolated system, our change in momentum is actually 0. Okay, so the whole impulse idea might not necessarily be an isolated system because you are getting a change over time in your momentum. But if you can define your system such that it is isolated, there is actually no net change in your momentum. And this is, of course, the law of conservation momentum. And that is just saying that the total momentum, big P, of an isolated system, that is important. An isolated system is constant. Interactions within the system, so remember that's going to be within our box of particles. Interactions within the system do not change the system's total momentum. Okay, and that's due to the action-reaction pairs. So what you start with is what you end with. All right, so I know we've done one quick example. Pretty much just pulled it from the textbook. I didn't want to walk through all the algebra because that would take forever, and I'm already at like 50 minutes in this video. So in the next upcoming videos for lectures 2 and lectures 3 about impulse and momentum, I'll do some extra examples. This video is just to focus on some of the concepts. So we talked about like generalizing the conservation momentum to lots of particles. It was super mathy. You don't have to worry about that, just as long as you know the momentum in an isolated system is 0, and you can actually use the conservation momentum PF equals PI. That's the big things I want you to take away with. And if you're still a little confused, don't worry, we'll do some examples coming up soon. All right, and if you have any questions, please let me know.